We've reached the point in the semester where we're actually going to start to do some programming in this class. So the first half, of course, we just did some Excel spreadsheets. So now we're actually going to generate some M files, which M is a .m extension, which works, of course, in MATLAB. So for the second half of the semester, you are going to either have to have a copy of MATLAB or a copy of Octave on your computer. As part of this, I've created a tool, which I'm going to show you here in a minute, that will hopefully help you with these projects and how to use the problem-solving methodology to solve them. So first off, MATLAB, again, costs money. Even the student version has a cost associated with it. Octave is an open source program that you can use to create M files just like you can in MATLAB. This is a screenshot of Octave. I have Octave on my own personal computer. I have MATLAB on my Valencia issued computer. They both will write M files. However, the one caution is there are some codes in Octave that do not work in MATLAB. Everything that works in MATLAB so far I've seen works in Octave, at least for codes that we will use in this class. So make sure you get that set up on your computer. There are links in the first week material for where you can find the programs and most importantly where you can find the help screens and the technical support if you have any issues getting it installed and running on your program. One caution, I've never tried either version on a Mac, but I have heard a lot of students have issues with it on a Mac, just for FYI. So here is my program checklist. You will find this in the first week's assignments for MATLAB and Octave. And this tool is the tool that I'm giving you to hopefully focus on the steps that you'll need to solve the problem. Typically what novice programmers do is they do this additive iteration of programming, meaning that they see the problem, they throw some code together, it doesn't solve the problem. So they add more code, still doesn't solve the problem. They add more code, still doesn't solve the problem. They get to a point where it's so complicated that there's nobody that could figure out what their code is supposed to be doing and why it's not solving the problem. So what's a better solution is to actually plan out your work ahead of time and then use a way to build your code from figuring out the steps ahead of time. That's what this checklist is going to do. This checklist and the material that supports this checklist, if you turn it in with a project, I will give you 5 extra points. However, you must turn in both the checklist and all the work that you do to support the checklist. And you'll see in a second what I mean by that. So this is the checklist in its whole. And let's talk about each part of it. So, first off, here's the example I'm going to use. I forgot about that. This is essentially the version of, this was the first problem from Excel. So what I decided to do in this particular case is kind of modify it. And I think I'm just using area if I remember correctly when I did this. So I'm taking 2 of the diameters and finding area. And I'm going to use that to use the tool to show you how to use this thing. So first thing to do is define the problem. So essentially what you're doing in this particular case is, in your own words, you're going to explain the problem that you want to solve. Why? Because there's been a lot of times in engineering where engineers solve a problem that isn't actually a problem. So in this particular case, the way I'm redefining the problem is I'm going to prompt the user to input a diameter of a circle and then calculate the area, and I'm going to use the formula area equals pi r squared, right? R is radius, of course, and diameter is double the radius. So there's my step 1 checked off. Step 2 is essentially listing all your inputs and outputs. Again, good practice to just come up with a list of what's going into the program, what's coming out. So the way I see it, we've got only one input in this particular case. We've got a diameter. I'm defining it by the letter D. Now MATLAB and Octave are case sensitive, so the capital D that I'm using here, I must be consistent when I write my program and use a capital D, because capital D and small d are completely different variables. The one and only output is area. So area I'm defining by the variable A. There are some variable names that are reserved, and you'll find those in the help sections for either program. Step 3 is to list all the equations that you're going to use. Well, in this case, there is only one equation. A equals pi r squared. Did I account for all my inputs and outputs? Well, it was a little tricky there in this particular case, right? My input was actually diameter. So I'd have to actually use the formula pi equals diameter divided by 2 squared rather than r squared. I'm catching an error that I made myself here. But list my equation, and now you can see the issue I have with it. So are there any logical decisions? Are there any ands, ors, if, thans, less thans, greater thans as part of this program? Or is there going to be any branching? Right? No, in this case, we're going to get an input value, and we're going to do a calculation, and we're going to export or put the output value on the screen. So that's step 4. Step 5, program flow. So there's 2 ways that you can do program flow. You can use a flowchart. That's kind of your graphical way of showing program flow, or you can use Pseudocode. Essentially, that's writing out the steps that you expect your program to take in English, right? And then you take those steps and you convert them to code. Same thing with a flowchart, right? You put each step in its own symbol, and then when you write the code, you take those symbols and you convert them to code. Right, this should include all your inputs, your outputs, any logical decisions. So if you do have something that's going to make a decision or something that is going to definitely loop, a flowchart's better. The Pseudocode is great for a real simple program. I'm going to show you both examples in this case. So here's step 5 for a flowchart, right? Start of the program, area of the circle. So I'm going to input the diameter. I'm going to calculate the area. I'm going to output the area. My program's done. Right, pretty straightforward. So that's a flowchart. Here's my Pseudocode, right? Start the program, get the input for the diameter, calculate the area, output that area value, and the program. So there's step 5. Step 6, verification. So how do you know if you did solve the right problem and you did write good code, how do you know the code's any good? So you need to do some calculations by hand to make sure that's the case. So you'll notice that I picked 2 of these values from the original Excel, so you can check these values in your original Excel spreadsheet, and you'll find that these 2 work out to the values that I've shown there. So if I put these values into my program and my program is correct, and I'll get these values, then I know my program's good. So I took this information and I put it into a program. So here is a typical M file built in Octave. So you see the percentage signs indicate that there is a comment, and this is one thing that is a requirement, that when you do write your code, you need to comment everything out. So you need to identify who you are, you need to identify what the project is, you need to put at least a minimum of a date in there. Then for each step along the way, you need to explain what it is in a comment. So for instance, the first step there, that's actual code, I'm assigning the value D to an input command, which means that the stuff that's inside of the single quotes will be put onto the screen, and it will wait for the user to input a value. There's no semicolon at the end. So the value D will be displayed on the screen to know that you put the right value in. So we're going to prompt the user to input the diameter in meters. Right? They can put it in light years for all you care. Right? The program doesn't care, but I'm asking the user to put it in meters so that the answer will come out in square meters. Right? So I do that. Then I've got my formula, and here's the formula in the correct form, as I mentioned, as we went through these slides, right? And now here's the correct form. The area equals pi times the diameter, D, divided by 2 squared. So, and I have my comment saying, perform the calculation for area. You could have put that comment on line 7 after the command, or you could put it the way I did on the next line here. I did that just so the screen, when I cut this and pasted it into the PowerPoint presentation here would look a little cleaner. Notice I have a semicolon at the end, which means that the area is not going to be put on the screen until I do it in the next step there. So the last step for the program is fprintf, which is displaying the values displaying the stuff that's inside of the single quotes and a value. In this case, the value is A. So the thing that'll be displaying is the area in square meters of the circle is, I'm doing a floating point number. It's going to be 2 decimal places. And I'm putting a new line at the end so that the next program I run will start on the new line. Otherwise, it looks a little messy. And the value A is what it's going to put there. So it's going to say the area in square meters of the circle is, and it's going to put the value in there, which, of course, my comment says displaying the results. So what does this look like when you run it? So I ran the file, I ran it twice. So you can see my program name was circle area example. And you can see on the screen said enter the diameter of circle in meters. In this case, I put in the 1.8. It told me I put in a diameter of 1.8, which is good because that's what I put. And it told me that the area in square meters of the circle is 2.54. I ran it a second time and it said, the program asked me to enter the value. I entered 10.8. And it told me that the area in square meters of the circle is 91.61, which corresponds to my hand calculations, which lets me know I've done it right. So there you go. So I will put this up in week 1, the checklist. And again, any project that you do for the second half, if you submit the checklist and the documentation to support the checklist, right, each of those pieces that I just showed you in this particular video, then you will get 5 extra points on each problem. So hopefully this tool helps, and feel free to ask any questions in the discussion area for MATLAB and Octave. Good luck with the projects.